All right. I don't know when the date for that is just yet. All right, light can be described as which of these? A magnetic wave, an electric wave, a longitudinal wave, A and B, or A, B, and C? These aren't your quiz questions, but just sort of jog your memory on some of these things. And look at your notes. You can ask a friend. All right, I'm going to stop at 45. 45. Right. B is right. It is a magnetic wave and it is an electric wave. It's an oscillating electric field and an oscillating magnetic field together. It is not a longitudinal wave. A longitudinal wave is like a compressional wave. It's a transverse wave instead. I'll post these questions online soon. What causes an electromagnetic wave? Moving charges, light energy, mechanical energy, an alternating medium, or virtual motion. Here we talked about both how radio waves and visible light are formed. So what causes these electromagnetic waves? I'm going to stop at 50 seconds. A few more seconds. Stop at 50. I'll go to 55. Or 3 seconds. Yeah, 55. Okay, moving charges. Remember with radio waves in an antenna, you have an electron that moves up and down the antenna, right, along that metal rod. For visible light, on the other hand, it's still a moving charge, but where does the charge move from where to where? For visible light, generally. Huh? You remember? Yeah, the orbits, right. The energy levels of an atom. Typically, visible light is caused when you have electrons that move from one energy level to another. What is the proper order of these types of radiation in order from highest to lowest energy? This is highest to lowest energy. Looking at gamma, radio, visible, and infrared. All right, I'm going to stop at 55, 55. C. That's right. C is right. What was E? E is from lowest to highest energy. Right? Radio has the lowest energy to infrared, visible, and then gamma rays. Think about the energies, right? You never put a source of radioactive material next to your head, right? Because the gamma rays that come off of that have very high energy, and they can cause damage to the cells in your body. Radio waves, we put a source of radio waves to our head all the time because this doesn't cause damage to our body, right? Your cellular phones, right? Like a banana phone. You ever heard that song? Banana phone from Rafi. You ever heard it? Seriously? Ring, 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 banana phone. You know what I'm talking about? You grew up with Rafi? You just know the song. Okay. The energy of an electromagnetic wave is directly proportional to which of these? The amplitude, the frequency, the period, or the duration? Directly proportional. So if this thing goes up, the energy goes up. Alice asked about the electromagnetic spectrum. I'm going to stop at 40 seconds. 40 seconds. B is right, frequency. I can see that you might think it's related to the amplitude, because when we were talking about sound, the volume of the sound was related to the amplitude. It's a little bit different with electromagnetic radiation. The amplitude doesn't have anything to do with the energy of the wave. It's the energy, it's the frequency that causes the energy of the wave to go up. By the way, it's not listed here, but what is the energy inversely proportional to? That is, if this thing goes up, the energy goes down. The wavelength, right? Because wavelength and frequency are inversely related. So if frequency goes up, wavelength goes down. If wavelength goes down, energy goes up. So they're inversely related. Okay. Visible light is caused by which of these? If you're listening, we said this earlier. All right, I'm going to stop at 30 seconds. Excellent. Hey, why did the coach go back to the bank? To get his quarterback, right? I like that. You like that, Brent? All right. A light moves from air to water. What happens to its speed? It moves from air to water. What happens to its speed? Does it increase, decrease, remain the same, or does it depend upon the amount of water that it moves into? I'll stop at 40. B is right. When it moves from air, where the index of refraction equals 1, to water, where the index of refraction is 1.3, the index increases. That means that the speed is going to decrease. Materials that have a higher index of refraction will have a lower speed. Right? You don't need to know the index of refraction for water, but you do need to know that for air, that the index is 1, and that you can't go any lower than that. Air is basically like a vacuum as far as light's concerned. Just a few more. Light is incident on a slab of glass. It's coming from air going into glass. Which of these describe the path of the refracted ray? Let me draw a little picture here, just make sure that you understand what's going on. I have air on this side, glass on this side. I have a ray that comes in. And this line, this is called the normal line. We mentioned this earlier, but the normal just means perpendicular. It's perpendicular to the surface. All right, so which of these describe the path of the refracted ray? Is it not bent? Is it bent towards the normal? Away from the normal? I'm going to stop at 105. Or go to 108. Okay, that's good. It is bent towards the normal. If it's moving from a low to a high index, it's going to bend towards the normal like that. You can imagine that you have these wave fronts. At this point, it slows down, and then that causes this side to speed around, right? Like a tank. If you're moving a tank, you speed up one side to turn the direction that you want to go. All right, light moves through a slab of glass. What is the path it would take? We had this one last time. So it's easy for you. Light moving through a slab of glass, which one will it take? D is along the same line as the ray. A is to this side and B is to this side. So if I have this slab of glass, which path would the ray take? All right, I'm going to stop at 35. 35. A is right. Good. Remember, it bends towards the normal when it enters this slab of glass, so it bends in this direction. And then when it goes out, it bends away from the normal. And it turns out that these two rays are parallel to one another. They're just slightly offset. Which of these best describe the index of refraction? N is greater than 1, greater than 0, less than 0, less than 1, or somewhere between -1 and 1. This would be the index of refraction for a medium, be it liquid or solid or gas. That's 110. I'll stop at 110. Just guess if you're not sure. Remember, on these questions, by the way, you do get credit even if you get the answer wrong. A is right. N is greater than 1. See, a lot of you put C and E. C, N is never negative. It's always a positive number. Likewise, that would get rid of E here. It's always a positive number. For a vacuum, N is equal to what value? Is equal to 1. And then any other medium, even air, we say that it's 1, but it's actually like 1.00 something. Right? So it's not exactly 1. So the index of refraction for a medium is always greater than 1. All right, we're going to stop there. We can come back and do these later. Write myself a note here. No. No. All right. See, last time we started on the eye, we talked about, we might actually finish up this chapter today, and then next time, probably we'll start on electricity, which is going to be the previous chapters. I know we skipped it before just because I didn't have my notes prepared for that chapter, but if you want to do reading while you're in PG or Disney World or in Cozumel, you going to take your book here? But if you do, you can read that previous chapter, that chapter 5, because we are going to do that chapter. And then after that, we'll go into chapter 7. Let's see, talking about the eye, we just started on the anatomy and physiology of the eye. So we have the eye as a sphere. It's filled with clear fluids, the vitreous humor and the aqueous humor. I'll show you where those are in just a bit. I guess that was it. Let me show you a diagram of the eye. That's not the eye. That's not the eye. Oh, there we go. So this is the eye. I think there was actually a figure in your book of the eye. Double check that. Is that true? Does anybody know? Yeah, you need to know the parts of the eye. You'll certainly have that on your test. And then also, let's see, do we have the ear on this test? No, that's the last bit, yeah. So, but you'll certainly have the eye on there, where you'll need to know the parts of the eye and what it does. Just double check this. This one. 197, thank you. Oh. Okay, I can send you this figure, or I'll send you the link for it. I snagged it off the internet. For myself. Okay, so we have 3 layers to the wall of the eye. I'll just write them here. Three layers. The first layer is the fibrous layer. This is the outside layer, and it consists of the sclera. That's this. This is the white part of your eye. Right, the whites of their eyes. So the white part of your eye, and the cornea. And the cornea is the clear part of the eye. It's right here. The cornea acts as part of the surface that actually bends light when it comes into your eye. So we have a separate thing that's called the lens, but the cornea also acts as part of the lens of the eye that moves light from outside of the eye onto the retina. The second layer, see, I'm going to write it over here. The second layer is called the vascular layer. This is also called the uvea. Is that how you say it? Y'all didn't cover this in A&P? Y'all don't remember. Is that right? Uvea. All right, so the vascular layer, and this consists of several things. The choroid, it contains blood vessels. Let's see, the choroid right here. The ciliary body. The ciliary body is right here, and then there are ligaments that attach to the lens. These are muscles that change the shape of the lens. And we talked about last time how that lens, if you're focusing on something far away and then you move it closer, that your lens has to change its shape, right, in order to see things that are far away or closer. And the ciliary body is what does that. So it has these muscles that will squeeze this to make it wider in the middle, or stretch it out to make it thinner in the middle. That's the ciliary body. And the iris. The iris is the colored part of your eye here. I'll show you a figure of it later, but it's basically an aperture. This prevents something that we call spherical aberrations. Spherical aberrations occur because spherical lenses don't all focus at the same point. And so the aperture, what it does is it blocks out light from part of the outer parts of the lens, which prevents spherical aberrations. Don't worry about that. That didn't come up in your book, right? Pretty sure it's not in your book. Y'all recall? Spherical aberrations? I don't think it is. All right, but it's an aperture. It also just limits the amount of light. So for example, if you enter into a dark room, what's going to happen to your iris? Right, it's going to open up that aperture, right, so that you can let in more light into your eye. All right, so that's the vascular layer. Consists of the choroid, which has blood vessels that brings nutrients to your eye, the ciliary body. Those are the muscles that change the shape of the lens, and then the iris, which is an aperture. And then, see, I'm going to erase some of this up here. The third layer is called the sensory layer. The sensory layer is the innermost part. It contains the retina. There's the retina right here. This part is the retina. And the retina converts light to an electrical signal. The retina contains rods and cones. Rods are for low light black and white situations. And cones are for high light. Not sure if that's the right term, but when you have lots of light, very bright lights, colored conditions. All right, so for example, when you go out in the early evening, the trees, which you know are green, they appear to you what color? What is that? It's dark. They just look dark. So like in the early evening, when the sun is going down and it's not very bright, things just sort of lose their color. And it's because your rods are being activated more because those are used for low light conditions, but they're also only for black and white light. So they can't detect the colors of a green tree or a pink flower in low light conditions. So you need your cones for that, but those only work in very bright light conditions, and those are used to detect color. People who are colorblind are missing some set of these cones. So you have different cones that are for different colors, and people that are colorblind, like my son is colorblind, he can't tell what like purple from blue or something. You too? Yeah. Thanks for admitting that. I was really sad when we found out. I don't know, it's sort of, I know it's not a big deal, right? Not a big deal. Yeah. But it's just sort of, it's like the first thing that we ever knew about our little child that was wrong. But that's not wrong, it's okay to go. But anyway, people that are colorblind are missing one set or more of these cones. They don't have them, or they don't function properly. The retina also contains the fovea. I'm going to erase this part over here. And the fovea is right here. This is just a place where you have lots of rods and cones. And you can probably tell why. Why would you need extra rods and cones at that part? At that point on the retina? That's where most of your light is coming. Because if you have light rays that come in, they're going to focus, or actually let me redraw that. They're going to focus at that point. So most of the light is going there. Other light is also on other parts of the retina, but most of the light goes to the fovea, and so you just need more detectors there. You also have on the sensory layer and on the retina is the optic disc, which is right here. And this is just where that electrical signal is all sent to the brain. So all those nerves in the retina, they combine to come here to the optic disc. And there are no rods or cones there. There's a blind spot in your eye, but you can't see it because your brain actually fills in the missing image. So it's like we're looking at one another right now, and there's just like one small part of the image that's missing, but your brain just fills in that. pretty cool, right? Yeah. So it takes information from the other parts of the image and fills in this part. It's not that big. I'm not sure how big it is, but all right. We also have two types of liquid in the eye. Can I delete everything on here? Yeah. Two types of liquid, the vitreous and the aqueous humor. One of these is replenished, one of them you're born with, and you keep your whole life. I always forget which it is. Let's see, the aqueous humor is between the lens and the cornea. So it is right here, I think, isn't that right? Aqueous humor. It's not labeled here. This is the aqueous humor. It's just a liquid that's in between the lens and the cornea. This replenishes and drains regularly. It brings nutrients, flushes out waste. That's the aqueous humor. You can have excessive pressure here, so you can have a problem, a medical problem, which is called intraocular pressure. Remember we talked about this when we had our chapter on fluids, when you had pressures in the body. What was the intraocular pressure? What kind of device did we talk about that measures the intraocular pressure? What was it? Yeah, it's an thermometer. Remember had that beagle in the vet, and they had that little pin that went out and punched his eye. And then your optometrist probably has a different device that actually shoots air in your eye. You ever had that measured in your eye? Does it hurt? It's weird, right? Yeah, so that measures your intraocular pressure. If you have a problem either with the flushing out of this, or the replenishment, or the drain, that is, it's replenished too quickly, or it doesn't drain enough, then you can build up that intraocular pressure. And that can cause, what does that cause? Glaucoma, right. So this is an excessive pressure is a result, or will result in glaucoma. So this is if you have excessive pressure. All right, and then the other is the vitreous humor. That's inside here. It helps to keep the shape of the eyeball. And it's not replaced. So this is as old as you are, 38 or whatever it is that you are. All right. So it just helps to keep that spherical shape of your eyeball, and it's not replaced. I have a little video I want to show you about this. It's like an animation, but it shows all these different parts of the eye and how they work. I'll send you guys this this figure of the eye. I'll send you a link for it. I just found it online. So it looked like I actually did give you the wrong location. Let me just go back and clarify that. On that aqueous humor, the aqueous humor is actually located, where was it? Like right in this area. Isn't that right? Just know that the vitreous humor keeps the shape of the eyeball, and then the aqueous humor is up around the lid, and then it drains and is replenished, bringing nutrients to that part of the eye. All right, let's see. We have a certain path of light into the eye. The video sort of talked a little bit about this. main point being here that the lens, that portion of the eye that refracts the light onto your retina, is an important part of the eye, but most of the refraction actually occurs when you go from a very low index onto the higher index, which is the interface between the air and the cornea. That's where most of the bending occurs in the eye, and then the lens just helps to further focus that light onto the retina. So most of the refraction occurs at the air cornea interface. Because that's where the indices of refraction are most different. Once the light rays actually get into the eye, it's traveling through a substance that's a lot like water, and so the index of refraction doesn't change that much. Now the lens is a little bit different because it has to be in order to focus the light onto the retina, but most of the bending of light actually occurs at the cornea when it enters the eye from the light. And they sort of mentioned this in the video, but for the aqueous and virtuous humor, the index of refraction is a lot like water. Just simply because the aqueous and the virtuous humor are mostly water. So the index of refraction for water is about 1.3. That's what it is for your eye. All right, can I go down from here? No? I'll wait just a second. Why did the pig leave the costume party? Yeah, why did the pig leave the costume party? Say, I don't know why. Because everybody thought he was a boar. Alright, a boar. Like a wild boar? Yeah. Alright, can I go down now? Yeah, alright. We can compare the eye with a camera, and your book goes into this a little bit. The main point here, when we compare the eye with a camera, you change what about the system? What do you change with the camera? So we have three things with an optical system. We have the object distance, we have the focal length of the lens, and we have the image distance. With a camera, what do you change? No, not for a camera. I mean, you can change the focal length of a camera, but you have to take the lens out and put in a new lens. Right? So that's really the only way you can change the focal length of a camera. What is it that we're going to change with a camera? It's not the focal length. It's the object distance or the image distance. The image distance, right? Yeah. Because, we move that lens back when we have an optical camera that zooms. I know a lot of our cameras don't zoom anymore because we use a digital zoom, like with your cell phones and stuff. They don't have a lens that moves back and forth. But with the point-and-shoot cameras and nicer cameras, the lens will actually move back and forth. That means that it's changing the image distance. So if we were to look at our system, we'd have some object here, a person, and then you'd have your lens, and then you have your film or your detector or whatever, where the image is being projected, and actually the image is upside down, but that's separate right now. All right, and so when we change this, we're actually changing DI. So with a camera, you change the image distance. So if you look at something that's further away or closer by, you're going to actually change the image distance with the camera. But with the human eye, what changes? Because you can't change the image distance of the human eye. That's set by the diameter of that sphere, the diameter of your eyeball. So what then do you change with the human eye? The focal point, or the focal length of the eye changes. So with the eye, the focal length changes. All right. Near and far point are the nearest and furthest points that you can make an image of the object. Or actually, the nearest and furthest points. The near point is the nearest point, the far point is the farthest point. The near point is set by how curved the lens can be. So take your finger. We'll finish writing this. And then take your finger and hold it in front of you. If you hold it out, a couple of feet, you can see it just fine. Right? Take your finger. And then move it in. And there will come a point, as you're moving it in, your lens is getting squatter and squatter and squatter. And then there will come a point where it's just you can't focus it. No matter what you do, maybe you can squint a little bit, but you can't. There comes a point when you can't focus it. Right? You can see, Kaylin, you can see yours way up there. Usually for a sort of a normal age person, like middle age, 20s and 30s, that near point is about 20 centimeters. So right about, this is about 20 centimeters or so. But as you get older, that near point gets further and further away, and you just can't focus on things up close. That's why old people are like this, right? Because you can't see things that are really close, because that near point changes. And it's because that lens, it just can't squeeze down fat in the middle anymore, because those muscles have to push down on that lens and make it wide in the middle in order to focus on things that are close. All right, so if you want to look at something close, that lens has to get really squat. It squeezes it down. The far point, on the other hand, is set by how flat the lens can become. And it's a lot easier for the ciliary body to make your lens flat like that than it is to squish that lens down. So we can see far away pretty easily, right? But it's just that near point that changes. Typically, the far point is at infinity, so typically you can see things an infinite distance away. And what that means is, the focal length of your eyeball is a centimeter or two, and that just means at a distance that's much greater than a centimeter. So like, the back of this room is basically infinity away in comparison to my eyeball, because it's hundreds or thousands of times the focal length of my eyeball, or across campus, or up in the sky, or whatever. So typically the far point is set by is typically infinity. And then, as I said, the near point, it can range from anywhere from 10 to 100 centimeters. So some people can see things like right up close like this, and then some people, they have to hold stuff out like this far in order to see it. So next time you see like an old person reading a book like this, so you know your near point is really long. And then they'll slap you or something. All right. That's the problem there. Let's talk a little bit about vision problems, and then I'll give you a quiz. So we have four vision problems. We have nearsightedness or myopia. We'll just do this one and then I'll give you a quiz. All right, and then we'll deal with the others later. Nearsightedness. This is also called myopia. Make sure that you know what each of these are and what causes them. So nearsightedness, the image forms in front of the retina. This means that your eyeball is too long. So whereas the eyeball is supposed to be pretty spherical, a nearsighted person might have an eyeball, that's an exaggeration, but they have an eyeball that's too long. So when the image forms, it forms like right here. And so what you get is just like a fuzzy image in the back, because those rays, they cross right here, and then they begin to diverge again, and so you get a real fuzzy image on the back. That's nearsightedness. People that are nearsighted can't see far away things. So the nearsightedness, that refers to things that they can see. They can see things that are up close, but they cannot see things that are far away. Not very well. You can use a diverging lens to correct for this. So if we have light that comes in and it would normally meet here, if we put a diverging lens, which looks like this, what that does is it takes that light, I'll draw it in blue here, or I'll draw it in pink. It takes it, it sort of bends it out a little bit so that when it crosses, it will now cross at the retina. And it's pretty easy to measure what type of lens you need. But for a person that is nearsighted, their eyeball is too long, they can't see far away things, and you use a diverging, also called a what type of lens? This is called a concave lens, right? So you use a diverging or a concave lens. Let's see, I think that's all. Yeah, we'll stop there. I'll give you a quiz. We will pick back up with this chapter on Tuesday when we return after Fiji, and we will just have probably 5-10 more minutes. I have a few more questions we'll go over for that, and then that day we will be in the next chapter, and soon thereafter we will have the chapter quiz, the reading quiz. So let's say that since we're just coming back from spring break, we'll just have it on that following Tuesday. All right, so don't expect a quiz the week we return, because I know y'all going to be recovering or whatever, but we will have a quiz soon after we get back from that chapter. All right? All right. Let's go and do our quiz. It won't take you 20 minutes, but hey, it's fine. Make sure you put your N number on here.